And here again, it does make sense to think about classical summoning, and classical summoning is also a non-trivial question for unconstrained tasks of this form. So in the classical version, she's given a classical state at the start point, way back. She can send it wherever she likes, but she's still potentially got a problem because her task is to return a copy of the classical state at precisely one valid return point and nowhere else. So she can't just blitz all the return points with copies of the state and rely on the fact that one of them's got to be right. She fails if she returns it to a state that isn't valid, or if she fails to return it to a state that is to a return point that is valid. And there's another little possibility and impossibility theorem, which certainly isn't immediately obvious and is quite nice to play with. It turns out that what's quantumly possible for these unconstrained summoning tasks is also classically possible, and maybe more surprisingly, the other way around. And this uses slight extensions of the things we've already done. So it uses quantum secret sharing again, and it uses Weidmann's distributed telecomputation. And maybe I'll skip the details here. I can discuss them if anybody's interested. So I find this foundationally interesting, as well as the obvious applications to distributed quantum algorithms and to quantum cryptography. Whether it's foundationally interesting in a sense that's important for black hole information questions, I don't know, but I guess if one doesn't throw the idea out there to people who are thinking about it, one never finds out. At any rate, it's a natural task. There are many versions of it, and lots of ones that haven't still been explored. Lots of interesting efficiency questions, which I haven't really touched on here. So far, all the theorems about possibility and impossibility rely on well-known facts about non-relativistic quantum information. It seems like quantum secret sharing in particular is telling us something, surprisingly, telling us something key about relativistic quantum theory as well as non-relativistic quantum theory. It at least begins to give us an answer about when and where quantum states are replicated in space and time, and shows it's subtler than one might have realized, and the answers are far from immediately intuitive. And it seems like a good starting point if you want to try and axiomatize relativistic quantum theory operationally. You want to think of this, what sort of theory is this? It's a theory in which these type of tasks are possible and these types of tasks are not possible. Well, the summoning tasks seem like excellent places to start in that project. And that's really all I wanted to say. So thanks very much for listening. Yeah.
I'm reckoning that nothing about what you said relies on the fact that you are in Minkowski space as opposed to a Kerr space-time, or anything at all about the quality of the space-time we're in. It's all
I think
just the causal line, and that's...
I think that's right, yeah. Unless I missed a subtlety somewhere, but I think that's right.
I could imagine something about I guess you need some sort of continuous thing if you need to be simply connected, right?
I mean,
if you say, like, I have a path from here to here, one from here to here,
I mean, if you have CTCs or something like that, then at least your notation gets more complicated. But yeah.
Could you go back real quick to the generalizations of the summoning task?
The last one.
It's not the classical version. Basically, my question is do you think that summoning and then this unconstrained summoning, are these tasks sort of like an exhaustive set of primitives for quantum information and cryptographic tasks in special relativity? Or is there some reason you would think that, or do you think there could be tasks that would tell us something else about quantum information and special relativity?
I doubt they're an exhaustive set. I think the optimistic view is that there might be some finite set, or at least finitely describable set, and these are maybe the first ones among it. The pessimistic view is that it gets more and more messy the more tasks you consider, and that there's no way of sort of reducing it to some set of building blocks. And I guess we won't know until we try.
Remember the idea of trying to get quantum theory from the possibility of key distribution and the impossibility of bit commitment.
Yeah.
I didn't think that went very far. There was something else they needed.
Yeah.
Some broadcasting also.
No, well, there were various versions. That didn't go very far, it's true. I may be wrong, but those... I love bit commitment, and I love the key distribution, and I think they're important, but they don't seem sort of fundamental things to say about quantum theory in quite the same sort of way as summoning might be. It seems somehow to be sort of closer to the bottom of what one wants to say about quantum theory and information. Now that doesn't mean anything like this will work, but it maybe makes me not completely depressed by the failure of those earlier attempts.
Are there any interesting computational complexity results in relativistic quantum info?
No, there are sort of, well, sorry. I don't know of any. There are sort of efficiency gain results, but they're sort of gaining factors of. Well, even things like, you know, you could get stuff from A to B in response to data, as summoning shows faster than you'd thought if you were just designing a network to do precisely that. But
I'm thinking something that was like a task that would be, you know, you can do it with polynomial resources, you know, with no speed of light, and with the speed of light it requires exponential resources or something like that.
yeah,
I'm just
I don't know.
Sure, just even classically.
So for
Because if you have some computation that requires communication amongst many processors, just because it requires many processors and they're all certain size, then they're not in the same place.
Yeah, it's Skynet and things, but I guess then it would.
is there a? So I'm not the right person to ask, but I'll ask. Is there a good relativistic version of complexity theory that's really well worked out? I mean, people talk about p-space and but
we didn't try, at least they tried like not a lot of time, somewhere in 1980 with Levin, just to develop a model in which what we call it causal nets, in which the computation somehow happened in space.
Minkowski space, or more general space time.
It was not time could be introduced only later in several possible ways.
Okay, so do I understand right? You have a model. Does it?
The model is essentially just a network in space-time. The computation itself is a network in space-time. Somehow, it's a kind of graph which the uniformity is somehow is introduced, required by the property that somehow if the causal neighborhood of 2 points is isomorphic, then somehow that isomorphism can be extended forward. And then
Can you? I'd love to get the references for that. I'd be intrigued. But and what do we know about complexity in that model?
No, I just kind of establish some kind of connections with the classical complexities, but we didn't really explore more this model. So the one with kind of more complex result in it is maybe not the interesting one, but what is really computable because in the input there could be all kinds of symmetries, and depending on that, actually not everything is computable. Let's say if the input is simply a a cycle, then if it has a prime length, then we cannot compute much.
Huh.
That's not interesting. But
Okay.